Swayam Prabha. Digital India. Educated India.
We will start now with carbon 13 NMR. In the last lecture we looked at how to analyze 1D NMR spectrum for protons. Now the next important nucleus in NMR for chemists is basically carbon 13. So let us look at how carbon 13 NMR spectrum can be analyzed, what are the details of carbon 13 chemical shifts and so on. So let us start with this thing, that we know that carbon 12 is not NMR active, and that is very clear because it has even atomic number and even atomic mass. So when you combine the spins in the nucleus, they basically pair up and the net spin of carbon 12 is 0. So therefore you cannot do any NMR with carbon 12, but fortunately for us there is an isotope of carbon 13 which has a spin half, and this is because the mass now becomes odd number, and according to the rules we saw in the very beginning, carbon 13 has a spin half, and C13, the only problem but is that C13 is pretty weak, very weak compared to hydrogens, and the reason for that is given here. There are two reasons mainly. The number one is the natural abundance of C13 is very small. So typically 1% of all carbons in the molecule will be carbon 13. That means if I take a collection of molecules, out of every 100 carbons, 1 carbon will be carbon 13. So basically it means 100 times less concentration of carbon 13 compared to hydrogens. That is one reason why the sensitivity of carbon is less, and the second reason is this gamma. So if you remember, gamma is basically related or helps us to figure out the population difference between the energy levels and the strength of the interaction of the magnetic field with the dipole. Therefore we know that for the gamma is small, the sensitivity will be low because of this smaller population difference. In other words, the polarization of carbon is much less compared to protons, and that is basically 4 times less. So the carbon gamma value is 4 times less compared to hydrogen. So therefore if you combine these two factors, you can see there is already a factor of 400, 4 coming from here, and 100 means 1 out of 100 is only carbon. So it is not 100% carbon 13, only 1%. So compared to proton is 100% 1H nearly, therefore it is 400 times less. But there is one more factor which makes carbon 13 even more insensitive, is when we detect carbon. So normally what happens is in 1D NMR we apply the pulse to proton and we detect the proton signal. That is the standard 1D NMR, proton 1 NMR which we have seen up to now. But if you do the same thing with carbon, we are going to excite or apply a pulse on carbon and also detect carbon. So for during detection, again the sensitivity of the gamma comes into picture, and therefore there are twice it has a problem. First, when you excite, the sensitivity is already low because the population difference is low, but when you detect carbon, then also again it is low because of this low gamma. So basically it is like a square, I mean 2 times gamma comes into picture. So we can say it is 16 times less sensitive when it comes to detection of carbon, and multiply again with 100, so it is about 2000 times less. In fact, actually if you see practically it is about 4 orders of magnitude carbon is less, that means almost 10,000 times less sensitive compared to hydrogen. So carbon is therefore very weak, many times weaker compared to protons. So therefore there have been varieties of techniques to improve the sensitivity, which we will see later on as we look at 2D heteronuclear NMR. So we'll now, but what is the advantage of this having, even if it is so weak, what is the advantage then of studying carbon? The advantage is the chemical shift range. You see the protons typically is about 10 ppm, 0 to 10 is what we saw earlier. In fact it is even 0 to 5 ppm if you ignore the amide regions. If you look at only the to aromatic, it is about 0 to 8 ppm. But look at carbon, carbon has a huge range which we will see of 200 ppm. It can in fact go even beyond this, it can go even to 300 ppm for certain type of molecules. So, this wide range of chemical shift possibility with carbon makes it very attractive, and we will see why it so, because of different functional groups have very nice spread in the chemical shift, and therefore, carbon 13 NMR is preferred even though the sensitivity is much less because of these factors. So, what is the range of this chemical shift? Let us have a look at that, but before we go into that, we should look at the frequency of carbons. So, remember carbon gamma is now small. So, we have to look at how the frequency of gamma changes with respect to proton. So, this is shown here. When we look at protons, we have let us say we have a spectrometer which is operating at 500 megahertz, then the magnetic field for that is corresponding to this value. How do we get this relation? Remember again the equation omega equal to gamma into B0. So, you can see if the B0 value which is based on B0 and gamma, you get the value of omega. Omega actually this is omega, this is 2 pi into omega, 2 pi into frequency. So, this is how we get the omega value. Similarly, if I change the magnetic field to a different value, correspondingly this will change. So, for a hydrogen atom, it is directly the magnetic field is directly related to the frequency, and the proportionality is omega is equal to gamma into B0. So, therefore, when it comes to carbon, your gamma is going to change. For a carbon, we saw in the last slide that the gamma of carbon is 4 times less compared to proton. So, therefore, when you multiply omega, when you use the equation omega equal to gamma B0, your gamma is now 4 times less compared to hydrogen. So, if hydrogen is 500 megahertz, you have to divide it by 4. So, you have to divide the hydrogen frequency by 4, then it will become 125 megahertz for the same magnetic field. So, this is constant because we are looking at a given magnetic field, but the frequency you see there is a big difference. The frequency, operating frequency of hydrogen is this much and for carbon is this much. If you look at now 600 megahertz, proportionately it goes down by factor of 4. If you look at 800 megahertz, it goes down by again factor of 4. So, everywhere remember, if you are working at a x frequency for hydrogen, x by 4 is what will be the frequency for carbon 13 at the same magnetic field. Okay. So, this is very important because when you convert ppm scale to frequency, we have to keep this in mind. For example, let us say that there is 2 peaks in proton which are separated by 1 ppm. Okay. So, that will be 500 hertz for proton, because remember that equation we saw in the last part where you just multiply this frequency 500 into the ppm difference, and that is a difference in hertz. But if you come to carbon, then the difference in hertz will be different, because there the same 1 ppm difference in carbon peaks will now correspond to 1 into 125, which is 125 hertz. So, you see the difference is reduced compared to proton. That means, proton is more resolved, more well separated in terms of hertz value compared to carbon. So, now look at the ranges of chemical shift which is observed. So, as I said, carbon has a very nice very favorable frequency range. It goes all the way from almost 0 ppm all the way to 220 ppm, and you can see that big range is what is very attractive when carbon's 13 spectroscopy is concerned. So, you can see in the beginning, let us look at these ranges as we go from top to bottom. So, in the top part of the spectrum, that is when it comes close to 0 to 30 ppm, we can include from 0 to 30 here. So, 0 to 30 ppm you have what is called methyl groups CH3, and very strong peaks comes between 0 to 30, and the same has similar to what we see in protons. Protons also, remember, the methyls comes always between 0 to 2 ppm. Now, you can see this part up from here to here is all corresponding to the sp3 hybridized carbons. Now, so second, the methylene groups, if you look at CH2, the carbon of a CH2, that comes somewhere between 20 or 15 to 50 ppm. So, this is typically the range of the methylene groups, CH2 groups in molecules. Now, if you go to methine, where is methine? Methine groups basically come at 20 to 60 ppm. So, this is typically the methane carbons are observed in biomolecules such as peptides and proteins. In amino acids, if you in amino acid remember, the alpha carbon in an amino acid is a methane carbon, and therefore, that carbon very typically comes somewhere between 50 to 60 ppm. So, that is for amino acids, but general range is about 30 to 60 ppm for methane carbons. Similarly, for quaternary aliphatic carbons. Okay, so, aliphatic, because this is an aliphatic group, for that the carbon can come somewhere between this ppm. So, next if you go to the next zone, so you can see we can divide this whole NMR carbon range into 4 different zones, which is shown broadly here. So, first zone was basically the aliphatic carbons, which are sp3 hybridized, and now if you look at what is called as the because of the electronegative carbons which are attached to an electronegative atom such as oxygen, halogen, they come somewhere in this zone. So, you can see here for carbon bound to oxygen, for example, in case of alcohols or esters and so on, esters, where there is a carbon attached to oxygen, then that particular comes somewhere between 40 to 80 ppm. And then if you look at halogens, also very much downfield shifted somewhere around 40 to 80, and same is for bromine. Of course, as the electronegativity decreases, it goes upfield. So, that is why when you say chlorine which is more electronegative, the range of chlorine is chlorinated, the carbons attached to chlorine is higher than that of bromine. Now, if you come to next the level, next zone, the alkyne carbons typically come here. There is another set of peaks which typically carbohydrates, when you go to carbohydrates like glucose, maltose, they will also come in this zone. Okay. So, that is another zone, and after 90 ppm there is a gap. So, there is typically a region where you will not get any peak in NMR, and that is 90 to 100, a little bit 105. So, there is about 20 ppm range where typically you do not see any peak. Then what happens is after this 100, 105 starts this C double bond C carbons, they start coming at this range, and the very popular very one in quark in chemistry we come across this aromatic rings, and aromatic rings are very prominently they come between 110 to 150. Typically 175 is little on the extreme, but typically 115 or 120 to 150, this range is what typically comes in the aromatic. So, if you get peaks in this portion of the spectrum in carbon, you can as well be confident that there is an aromatic ring present in the molecule. So, we will use this ranges as we go along, as we analyze some more NMR spectra of carbon. Then comes the very important the amide groups, now not amide, sorry, carbonyl groups. The carbonyl groups, remember, can be part of any of this. It can be an ester, it can be an amide in the carbonyl amides. You can have anhydrides, carbonyl groups, acids, carboxylates. So, you see there is a very clear, this whole zone you can see very clear distinction that these esters, amides and anhydrides, they come somewhere in this range, and if you go a little bit downfield, you have the acids, that carboxylic acids which come in this range. Now, if you look at ketones and aldehydes, they come a little bit even more downfield. So, you see the ketones typically come very much downfield, that is the last, it comes around 200 to 220 ppm, typically are some more than 200, and aldehydes are little bit upfield shifted and they come between 190 to 200. So, any peak which you see from 190 onwards has to be either aldehydes or ketones. Typically, if it is much very high downfield beyond 200, then it is most likely a ketone. So, you can see that very nice distribution of chemical shift across a huge range of carbon, which can be exploited or which can be used when interpreting or analyzing carbon 13 spectrum. So, now let us look at these broad ranges. So, you see this is what typically you can think of, instead of thinking of a full range from 0 to 220, you can divide, as I said, into 4 categories. The first category is C double bond C, we can see that is comes 0 to 50, then you have the C single bond O. So, C single bond C is 0 to 50, that is aliphatic carbons, C single bond O is 50 to 100, then C double bond C, which includes ethylene as well as aromatic groups, always in this range, and then finally all the carbonyls are in this range. So, you can see there is a broad classification of the chemical shifts, and this is very useful. Typically when we do this solid state NMR of many materials, when you look at materials science, materials chemistry, typically many times we just want to have a broad quick picture of what are the functional groups present in the sample in the molecule. At that time we just record a 1D carbon spectrum and then see the based on the peaks present in the different zones, we come out with a hypothesis of what are the functional groups present in this molecule. This is a broad range. Now, let us look at the J coupling. So, we have looked at the chemical shift values in case of carbon. So, now let us come across look at the J coupling. Now, in J coupling you see that one thing you have to keep in mind is that the very low natural abundance of carbon. The carbon, as I said, is about 1%, means 0.01. So, that means if I have 1% carbon, the probability that I will find two neighboring C13 carbons will be 1% of 1%. So, which is 0.01%, very low, that is 0.0001. So, that means 1 in 10,000 case only I will find the two neighboring carbon atoms, both of them are carbon 13. That means you can never have practically two neighboring carbons as carbon 13 in at natural abundance. Remember, you can always generate a carbon 13 labeled molecule. In fact, these carbon 13 labeled molecules are available commercially, and in biology, as we see, we will see along, as we go along, we will see that in biology you need actually enriched carbon 13 samples. So, not in that cases, we are talking about a case where there is no enrichment. You are taking a standard sample, let us say from natural sources. In nature, you will not find carbon 13 enriched samples, you will find carbon 12 and carbon 13 will be at natural abundance. So, in such samples, the chance that you will encounter two neighboring carbon as carbon 13 is very low. So, therefore, practically we never bother about C13 coupling in carbon 13 NMR in natural abundance. But if you look at protons, there is definitely a coupling there. Why? Because you take any carbon, it is always will be attached to proton unless it is a carbonyl. Unless it is a carbonyl or a quaternary carbon, without except these two, all the carbons are generally attached to protons. Now, protons is 100% proton is NMR active. So, that means if you take any carbon 13, it is always attached to proton. So, in such cases the carbon proton coupling now becomes active because both are NMR active. So, there is a J coupling between them, and that J coupling is definitely present in your sample, and that is very common, means it is always there. So, that is a big problem, or again you can think of it in both ways. So, what typically is done, we try to get rid of this coupling, because the coupling can create a little problem when you look at the data. So, we will see that how it creates a problem. So, this is a thing we have to now take into account, that is that proton to carbon coupling is very much present in any molecule. So, you should always remember that proton 30, whenever you look at 13C, carbon is always attached to proton, except those two cases which I said, that is carbonyl and quaternary carbon. Except those two, all the carbons are always having a hydrogen attached, carbon 13. So, therefore, you have to worry about this coupling. So, now let us look at how this coupling pattern will be. So, typically the one bond C13 proton coupling means the directly attached proton to carbon coupling will be of this range 120 to 180 hertz. So, you can see this is a pretty large value compared to what we saw in the proton-proton coupling. So, if you recollect the proton-proton coupling values, it was in the range of about 5 to 10 hertz, sometimes maybe 20 hertz, but not beyond that. Whereas, carbon to proton coupling, and we are looking at one bond, whereas in the case of hydrogen coupling, it was 2 bonds for geminal and it was 3 bonds for vicinal. So, the geminal and vicinal coupling were of the range of 5 to 15 or 20 hertz. But in the case of carbon, we say it is directly one bond coupling we are looking at, and that comes in this big range, is a very big value about. So, what happens is typical, the n+1 rule is applicable here also. So, suppose I have a carbon like a methyl group which is attached to 3 protons, and then that carbon signal will be split into 4 peaks because of the I+1 rule, n+1 rule. and we saw that n plus 1 rule, if you use the Pascal's triangle, you expect a quartet. A quartet will be 1:3:3:1. Now, if you look at a methylene group CH2, then there are 2 hydrogens. So, according to the n plus 1 rule, you will get a triplet, which is 1:2:1. And similarly, if you have a methine group, then you will get a doublet, which is equal intensity 1:1. And in case of a quaternary carbon, or if it is a carbonyl, you get only one peak, because there is no coupling to any hydrogen. Now, in a way coupling you can say is very useful, because if I get a quartet, immediately I know it is a methyl group, or if I get a triplet, I can say immediately methylene. So, this coupling has a good information, has information about the type of carbon. We use the word multiplicity. So, multiplicity is the number of protons attached to a carbon. So, here the multiplicity is 3 for this carbon, multiplicity is 2, and multiplicity is 1, and multiplicity is 0. So, by looking at the coupling pattern, coupling multiplet, in principle, yes, it is a very useful information, you can get the multiplicity. But if you see, the number of peaks have increased, it has 4 peaks instead of 1, and remember the couplings are large here. So, when a coupling is large, this separation between these multiplet is also large. So, that means it occupies a large range of chemical shift, unlike protons. In protons, what happens is they occupy a small range, because the couplings are small. So, they are all together bunched up, but in carbon the separation is more, because J coupling is more, and therefore, it can create a problem of overlap, means 2 neighboring carbon atoms will start having overlap. So, let us see that how that can help. So, this is a case of ethanol. In a ethanol molecule, we have CH3 CH2 OH. So, the CH3 peak, the carbon of CH3, remember, comes somewhere between 0 to 10, which we saw, and because it is a CH3, then therefore, it should be a quartet. So, I am sorry, there is a label here, this is CH2, and that should actually come here. This is for the proton spectrum, but this by mistake it has to be reversed. So, this is for CH3, and that is the carbon spectrum, and that will come here, and CH2 will come here. Why does the CH2 come at 60 ppm? That comes because of the attachment to oxygen. So, with the increase in number of carbon atoms in a molecule, so in this case there are only 2 carbons. So, therefore, there was not a big problem with this coupling, the couplings were well separated. But it can happen that in a large complex, in a large molecule where there are many carbon atoms, this J coupling can be a problem. So, we will see an example how it becomes complex, and then how do you remove that interaction? We can remove that interaction. What we can do, we can get rid of this coupling multiplet and only get a single peak instead of a multiplet. That is possible, and for that technique what we use is called decoupling. Decoupling is basically a method to remove the J coupling interaction between carbon and hydrogens. So, this is basically what happens. So, you see origin of peak splitting is, remember we discussed, is because of only J coupling. So, let us say you have a proton A attached to a carbon B, which is C13, then what will happen is this proton will get a doublet. Why does it get a doublet? It has a doublet because it is attached to C13. So, remember C13 is a spin half nucleus. So, it has an alpha beta state, and because of that alpha beta state, this hydrogen will be split into 2 peaks. Similarly, if I look at the carbon, the same thing will happen. In case of carbon 13, it is attached to a hydrogen, and this hydrogen has 2 possible spin states, alpha and beta, and because of that 2 spin states, this peak will become doublet. Okay. So, that is why that is what I was saying earlier, that is a mutual reciprocal interaction, means if a carbon splits a proton into 2, a proton will also get split into 2 because of carbon. Okay. But what happens most of the time, this hydrogen is attached to C12, because remember according to the natural abundance 99. So, we can look at it like this. So, we can look at it like this. So, a proton is attached to C12 99% of the time. Therefore, it will give a singlet. Why? There is no coupling, no J here coupling. But for 1% of the molecule, this proton is attached to C13, that is for 1%. So, this will be a doublet because of J coupling. Okay. So, that means in any given molecule both of these are present. So, you have to add these two. So, if you add these two, what you will get? You will get a small peak and a tall singlet and a very small peak like this, because this height, this is now corresponding to 1%, whereas this is 99%. So, this is about 100 times taller compared to these small peaks. So, we use the word satellites. So, this is called a satellite peak, satellite peaks. Okay. So, this is what is the case in the case of hydrogen spectrum. So, this is a hydrogen, but this is not the case in case of carbon. If you look at carbon, in the case of carbon there is basically a proton attached to C13, but if you see this C13 is always attached to proton, right. So, anyway C12 does not give any peaks. So, C12 does not give any peaks. So, whenever you look at carbon 13, all the time this carbon 13 is coupled to a hydrogen. So, therefore, carbon 13 will always give this spectrum. It will never be a singlet, never a singlet, unless we remove the J coupling. Okay. So, that means that you have to keep this in mind very carefully. The point is that in the case of hydrogen spectrum, we do not see a coupling, we do not see the doublet, mainly because the 99% of the time it is a singlet because of this C12, but 1% of the time it is doublet. So, when you combine these two, you get a very small satellite peak, but not in the case of carbon. When you look at carbon spectrum, it is always attached to hydrogen, right, because C12 can never be observed in carbon in NMR. So, therefore, in the case of C13 it is always doublet, never a singlet. So, that means if I have to decouple, I mean if I want to get a singlet, means like this, if I want to get a peak like this, then I have to remove this J interaction. Only if I remove this J interaction, then only I will get a nice peak in the center. But remember, if I remove J interaction, I lose also information of the multiplicity. But let us say that we do not care for multiplicity now, we only want a single peak. If we want, then I have to remove this interaction between the J coupling between the two proton, this carbon and hydrogen, and then only I will get a. So, how do we actually do decoupling? How do we remove this interaction so that we can get a singlet? And that is done as follows. What you do is you apply a continuous RF irradiation is applied to spin A. Okay. So, we are looking at here. So, we want to decouple these two in a carbon spectrum. So, we are not looking at proton now, we are looking at carbon spectrum. So, in a carbon spectrum the doublet is coming because the proton has two possible spin state. So, how do I remove this doublet to singlet? One way is remove this alpha beta distinction. So, how do I remove the distinction between alpha and beta? Keep the population of alpha and beta level constant, same. That is, how do I do that? I can apply a radiation. If I apply an RF radiation on spin A, which is hydrogen, continuously. Okay. So, when I do that, the nuclei, the population shifts between alpha states. Why does it shift? Because remember, according to we saw in the very beginning, that when you apply an RF radiation which is equal to the energy difference, the molecules will jump from alpha and go to beta and vice versa. So, this process will keep on happening, alpha going to beta and back will happening if I keep on applying a continuous radiation. So, basically what I am doing is I am equalizing the population, means earlier it was a Boltzmann population, but now it will be equal. So, when the population becomes equal, for the as far as carbon is concerned, it does not have any different now between alpha and beta, because alpha beta are now equal. Therefore, it does not see any difference in the spin state. So, when that happens, this peak becomes a singlet. So, this process of doing an RF irradiation on one sample so that it removes the J coupling is called as decoupling. There are varieties of decoupling available methods in literature. So, therefore, decoupling in fact is a very ongoing part of research in NMR. The reason being what happens is you want to get a very nice decoupling, you do not want to get a half done decoupling. So, therefore, you need to apply radiation in a very proper manner. If you apply too much radiation, it will cause the heating of the sample. So, heating of sample is not good because your sample will not be stable. So, how do we apply a low power radiation so that we get a good decoupling is a process of an ongoing work in research in NMR. So, basically what happens in the end when you do decoupling, the J coupling information is gone, because remember, if suppose I have, let us look at again this picture. So, basically if I look at this will give me a singlet. Sorry, if I do a decoupling, this will basically become a singlet. So, I have lost the multiplicity information. So, this information is lost. Now, suppose I have, this is for CH, suppose I have CH2, there I expect according to the n+1 rule a triplet, but again if I decouple, I will get basically a singlet, and then that information is also lost. Okay. So, in this manner, if I do decoupling for every carbon, I keep losing the information of its multiplicity, but I will get definitely a much cleaner spectrum which is a singlet. So, we will see that how the multiplicity aspects can be recovered by some other techniques, and we will see some example of how decoupling improves the spectral resolution in the next class.